Hello everyone, Assalamu alaikum warahmatullahi wabarakatuh. This will be a recorded lecture, or we call it as a synchronized lecture for topic large-scale production for biopharmaceuticals. So first of all, what do you guys understand about biopharmaceutical industry? I mean, we learned what is biopharmaceutical from all the topics previously, but what exactly what we call it as biopharmaceutical industry? If we look in terms of the definitions, biopharmaceutical industry are in an industry that involve a multiple disciplinary of sciences, including chemistry, we have biology, we have biochemistry, we have biomedical, even medical itself, and those knowledge are actually related to medication in order for us to have some products related to biotech and even related to drugs, etc., etc. And those are exactly work or the professionals in biopharmaceutical industry. They are usually using what we call as data analytics in order to evaluate the current method of certain products, or even how exactly that they can improve available commercialized product in the market. So example of commercialized production of biopharmaceutical, we can find certain type of proteins, even peptides. There will be some enzymes as well, and even carbohydrates. So these are some examples, not just limited to four, but these are some examples that you can find commercialized product related to biopharmaceuticals. There are so many approaches that we can use related to biopharmaceutical industry, but mainly or generally the biggest approach in order to have a product related to biopharmaceutical is related to industrial microbiology. So what exactly industrial microbiology? I think this topic is more like not really new to you guys, but mainly a refresh what you guys learned back in the pharmaceutical microorganism, which most of them are refresh courses that I put in this lecture notes. As I mentioned earlier, the biopharmaceutical industry involves multidisciplinary knowledges and even approaches, but not just limited to what we call as the pure science, chemistry, biology, etc. But also you can see that involve engineering, like process engineering, or even those in mathematics also involved in this industry, even the computer technology involved in the industry. Okay, in general, when we talk about the biopharmaceutical industry, or even in generic industry itself, we can divide the processes or the approach into two stages. The first one, what we call as upstream processing, or USP, and the second one is downstream processing, or DSP, which I'm going to explain these two after this. Okay, the USB that I will explain to you guys is really related to industrial microbiology. It's not any generic of USB, because I think in pharmacy, compared to engineering, which we learn in January instead of USB, but then this I'll bring you guys specifically related to industrial microbiology. So under USB, for industrial microbiology, we can divide into 3 points that we're going to have a look. The first one we call as the producer microorganism. Second one is the growth medium, and the third one, the fermentation process itself. So when we talk about producer mechanism, we are talking about how to choose the best industrial scale microorganism in terms of their strain type, their characteristic, the properties, and etc. etc. As for the growth medium, we need to find the best medium that's suitable for the selected microorganism that we're going to choose for our production, and of course not just the best or suitable for the microorganism, but of course, because we talk about industry, we talk about cost effective, we talk about optimization, because in industry what we're going to do in terms of product, commercialized product, we want to have the lower cost as much as possible, but the higher yield and quality as much as possible. So it might be different, no, it's totally different compared to what we concern back in the laboratory scale, which mainly we talk about the real purity, the best yield that we want to have, but cost point of view, it's not much a big factor. But in commercialized point of view, cost is really a big factor in production, because of course you want to sell your product, right? Your pharmaceutical product out there, so you want it to be accessible for your targeted stakeholders, I mean your customers, so that they can buy your product. You don't want to sell a product that's too expensive, that when we talk about sales point of view, very low, so you don't have the much margin that you want to achieve in your commercialized product. Again, the third one, the fermentation, is we talk about what type of fermentation we're going to choose in terms of the process, into the type of fermenters we're going to use, etc. So I wish all of these 3 points I'll explain in detail afterwards. Under the downstream processing or DSP, the things that we're going to have a look into of after the fermentation process, I mean post-fermentation process, which we talk about cell harvesting or cell destruction, and then the purification of the product from the cell extract, and also the finishing step. I mean, like your finishing product, what will be your end product will be. That's really under the DSP. So compared with USP, is mainly up to selection of until fermentation. DSP itself, we look at post-fermentation processes. So with the DSP, things that we really need to pay attention is first, the method we're going to choose for purification must be rapid, must be efficient, and of course, there will be some byproducts or the waste coming from the fermentation process. So we want to ensure that whatever the waste that coming from the product we want to dispose is, they are safe, also an expensive process the disposal, to ensure that it will not incur further costs or further treatment to be done, which can affect the end product, I mean the price of the end product itself. Okay, now let's look into details, firstly under the USB, which we look into the producer microorganism. So when we talk about the microorganism that we're going to choose for the industrial steps, first we need to isolate the best or the suitable or the optimized industrial microorganism that we're going to choose. Mainly, we are looking from the environment, not from the pure cell line. Which there are two approaches in terms of isolation of this mechanism from nature. First step is using a shotgun, which is exactly, and the second one is objective. So what shotgun means? So shotgun means that we are taking samples from living organism or biofilms or other biomedical communities in the nature. So you can find them in animal, plant material, even in soil, in sewage, even in the water, even the man-made or natural habitat as well. So that under the shotgun. So under the objective approach, where exactly like we look into specific site of nature, which going to meet the objective of characteristics that we need to find or we need to have for our production process. And usually for objective approach, we look into the microorganism from natural microflora and we isolate from them. Of course, as I mentioned just now, it's not just a matter of microorganism. Okay, you got it, but then you need to grow it, right? So that's come the next step, what we call as the growth medium. So there are a few factors or conditions that you need to take an attention in order to choose the growth media for the microorganism that we're going to use in this fermentation process. So first thing that we need to do is it can help to isolate the target microorganism because we're taking from nature. So when taking sample from the nature, they are called as dirty sample because they are not just what we want. There are other type of microorganism in that sample. So we need to ensure that our media are able to isolate our targeted microorganism. Second, the media itself able to kill or even repress the proliferation or the growth of common organism or other organism that we don't want in our process. Okay, so it's not just isolate targeted microorganism. The media is able to kill and or repress the growth or proliferation of that unneeded microorganism. And the third is the media can encourage the growth of our targeted microorganism. Okay, so this is where in terms of encourage the growth, we're going to use a specific enrichment culture, enrichment media in order to allow or promote the growth of targeted microorganism. So when we talk about this particular type of media, it encourages the growth of the organism, and of course it increases the quantity of target organism. So meaning that growth and quantity. So meaning that it helps to split faster and in order to achieve a higher number of per number of the cells that we want to use further ahead. Okay, so these are the important points that we need to put in attention in order to choose the best medium for our industrial microbiology step. Okay, we already have our sample. We allow it to grow in the media that we choose, and then the media help to really promote, encourage growth, and increase the numbers. At the same time, kills or repress or suppress other unneeded microorganisms. And of course, the culture that we got it from the process, we need to screen further ahead. Okay, why we need to screen this? We need to make sure that the culture that we got can produce a specific enzyme or products that we want to have through the fermentation process. And of course, we need to check the inhibitory compound, the stability. We don't want that we have it, the pure the culture that we got it, but unstable after a while it dies. So we don't want that to be happen. Of course, we want it to be non-toxic, because if it's toxic, then it will affect the post-processing afterwards, especially when we talk about disposal or the waste management. And in this step, however, we're not really concerned much about the level of activity or even the concentration of a target product, because like that one will be improvised further ahead in order to make the fermentation process faster, or you want to make a high yielding for the targeted product in the whole process. But that will be the further step ahead, but not in this step. There will be some questions just to answer your concern. Perhaps, okay, we take from natural sample, right, from the wastewater, from the soil, etc., etc. But how do we know that exactly the sample that we have? So you need a control to confirm the targeted microorganism that you got is the correct microorganism that you want to use. So how you want to control that? So that is what we call it culture collections available throughout the world. Okay, so there are huge number of culture collection. I've written here there are more than 500 available throughout the world. Okay, so this is actually a purified culture of the cells or microorganisms that we can use as a control for industrial process. So they even have a catalog, they even have mentioned how to grow it, how to culture it, etc., etc. So the common that people use, mainly in Malaysia, we have other countries as well. One that got from UK, we call it National Culture Collection, UKNCC. And another one we call it from US, from the States, we call American Type Culture Collection, or ATCC. So from my own experience, I usually use pure culture from the ATCC because, as mentioned here, that covers all types of microorganisms. So not just bacteria, not just fungi or algae, etc. They even have the mammalian cells that we can use further ahead in our studies. So these are some examples. So we use this as our control. And then we compare the one that we isolate from our natural or environment sample, and then to ensure that okay, this meet the requirement as what the pure culture said. So that can assist us to whatever the microorganism that we can use is actually the correct microorganism as the control mentioned it is. Okay, the culture collection is not just to be used as control. So as we use it as a reference, so meaning that it's kind of a cell bank, which we can ensure that the type or certain strain of the microorganism is still there. So meaning that if you can't find it in nature anymore, like we said, I mean the easiest services goes to extinction, so we still have in the collection. So that's to maintain the strain or the collection. And of course, because it's work as cell bank, whatever the new strain that people found in nature, they can purify it, isolate them, and then keep it in the bank as well. Okay, so of course, as I mentioned earlier, having a control from the pure culture is good as reference, because then it can reduce the cost in terms of to confirmation of the isolation process from the natural sample. And of course, because it's a purified sample, it will give the optimized characterization properties of the culture itself. So meaning that if you see something wrong with your natural derived sample, you can compare it back with your cells that you got from the culture collection. However, people will not use pure samples or pure cell collections pure cells from this culture collection in industrial level. The reason why it is so expensive. Okay, I'll give you an example. For my current research group work, we use the cancer cells. I mean, the cancer cells that we got, I mean, per vial is costing you a minimum 2 to 3,000 ringgit per type of cell, which is one vial. So can you imagine that you're gonna do in a very large scale in a factory to produce enzyme, for example? You don't want to mainly put all your money or all your financial resources just to buy the cells. Then whatever the product that you got later, it will be too expensive. Even I should say only the top tier of T20 available to buy it or to use it. So that will defeat the purpose of we call it cost saving and so forth. So you may find in this table, these are some of the culture collection available in the world. They're from States, Netherlands, France, etc., etc. So you may read this just to see what exactly their whole interval mechanism in their cell banks. As I mentioned earlier, we don't use pure cells or pure strains from this culture collection because it's too expensive. So we always take the mechanism as we do, isolate them from the nature or from the environment because it's very cost saving, or we call it cost appropriate. But there are a few requirements that we need to meet in order for us to use that particular microorganism. First of all, it must be genetic stable. Okay, the reason why we don't want it to have mutation afterwards, because like it will affect whatever the targeted product or even the byproduct itself. So we want to ensure that it's genetically stable. And second one, it can produce efficient target product. So if say it can produce, for example, antibiotic A, okay, but the yield only like 5%, but 95% byproducts. So it still can produce the targeted product, but then it's not the major. The targeted product becomes the byproduct because 95% are byproducts, so that's not suitable. And of course, we want it can grow with limited growth factors, or there's no need to add additional growth factor to promote the growth. So meaning that they use as simple as of the media instead of a very complicated one. And then it's just inclusive of using a low cost of carbon resources and so forth. And because like there will be a lot of improvement we want to do in terms of, for example, increase the yield of the product or increase the process or simplify the process. So you want the microorganism itself is easily being manipulated or modified genetically. So I mean that it's easy for us to do some genetic engineering towards the microorganism. And of course, we want it to be safe. It should be non-pathogenic, and it should not produce any toxic agents unless your targeted product is toxic agent. For example, you want to produce venom or anything that used to kill something, I mean medically, so then you might want it. But then in general, we want it to be non-toxic, safe and non-pathogenic. And then it can be harvested immediately from the fermentation, meaning that after you ferment, do the fermentation process, the cells can be harvested immediately rather than further step ahead, further treatment ahead need to be done in order to harvest it. And of course, if your target product is inside the cell, or we call it intracellular, the cell itself or the microorganism that we choose can be easily been lyzed, meaning that you can break the cell wall easily or cell membrane easily, so that you can take the target product. But some of the process, the target product will be in the media itself, not inside the cell. So that should be fine. But then if your target product intracellular, then you need to ensure that it easily can be break out. And then last but not least, of course, we want to be the highest yield as much as possible of your target product, aka your byproducts will be very low amounts, because like if you have so much byproducts, meaning that will incur further cost into for waste disposal, how to purify them ahead. So we want to make sure that the mechanism that have been chosen or been selected have very limited of byproduct. Of course, the ideal no byproduct, but then we're not living in utopia, right? We're living in the real world, so there will be byproducts, but then we want it to be as limited as possible. So I did mention previously, like there we need a room of improvement for the selected microorganism because, for example, the first step, I mean your first prototype or the first process, okay, they can produce this 65%, for example, of a target product. But then we want it to increase further ahead, so meaning that we want the some kind of improvement to be done for the industrial strain. So, uh, so what are the reasons we want to improve the industry, not just in terms of the targeted product? We want to ensure that it can reduce the production and manufacturing costs, meaning that higher yield, but of course much simpler step from the USB, also the GSP side. So then you reduce the manufacturing costs, but higher yield, then you can provide or supply your pharmaceutical products at a much cheaper cost, meaning that more people have more access to your commercialized product. Okay, what kind of improvement that we can do for the industrial stream? So of course, we want it to have a better rapid growth, a much stable in terms of genetic stability, to be less and less toxic to the human, and of course, like if you can increase the cell size, it will be help us in terms of the production, the purification process afterwards. And we want the strain itself not to be so manja, or like need to be so much care of it. So meaning that it can survive, can use, have the ability to use cheaper substrate. Meaning that we don't need to use pure substrate, we can use any other substrate in order to grow them. And of course, other strain we can do, we can modify their submerged morphology. That's also will help in terms of the production process. And of course, we want it to do some improvement in terms of the post downstream processing, meaning that if we can eliminate the production of compounds that can interfere the downstream processing, that will increase our pure yield or pure sample as well. And of course, we want to improve in the mobility alteration in order to increase the product aspect rates. And last but not least, for example, like your fermentation process can only produce one targeted product, so we want it to, how about like it can produce two or three uh, more numbers of product from one fermentation process. So that's also meaning that you can kill not just two birds, many birds with one stone. So one less manufacturing cost but more product and higher yield, that will give you higher margin in terms of when the product being commercialized. In terms of methodology or approaches that we can do in order to improve the strain, in general, there are three of them. First, we call it natural recombination, meaning that easy to say, like when you do in terms of kawin pokok, meaning that you do some natural recombination process. Or the second one, what we can do, the step what we call it mutagenesis. So mutagenesis is actually what a process where exactly we modify the genetic information of organism, which result in a mutation. So not all mutation is bad, okay? Certain mutation can improve into the production of your targeted product or reduce the byproduct itself. And last but not least, which is really common nowadays, we do genetic engineering, meaning that you modify in the genetic level to meet your requirements of your process. Now let's look into the fermentation process itself, or what we call it pharmaceutical fermentation. Okay, why I mentioned pharmaceutical fermentation? Because fermentation industry, it covers many point of view. So you can find in food technology, you can find in engineering technology that's not related with the pharmaceuticals. So, but in general, the process is quite similar. It's just like whatever the products that you want to produce through the process will be different. Okay, when we talk about pharmaceutical fermentation, so especially in the pharmaceutical industry, they use or cultivate microorganisms or other organic material that we can use in order to produce pharmaceutical products. So example pharmaceutical products that we can find through this process, it can be antibiotics or therapeutic proteins or even enzymes, and even insulin can be produced through this process. And fermentation itself, we actually carry out or conducted them in temperature controlled tanks, or what we call it as fermenter. So what exactly, like in the fermenter we add certain nutrients or certain material to maximize productivity of our organism to achieve our specific objective, which our targeted product. So this kind of huge tank which have mixed everything around inside it, and then afterwards we can have our products later. Okay, now let's look into the fermentation process. Of course, we have the microorganism, but we need to look into the fermentation media itself. So in terms of formulation, how we choose it based on stoichiometry for the growth and also the product formation. So these two point of view is really important for us to decide. Okay, the consideration of the input that we need to really take really important, which the carbon nitrogen resources, the mineral oxygen that we're going to use, how about the conversion to cell biomass, and also we need to look into the metabolic products, the carbon dioxide, and how much water and heat that we need to provide into the fermenter itself. Okay, so there are a few different levels of fermentation that we can find. So first of all, we talk about small-scale laboratory fermentation. So in this case, we only use pure chemicals because like we want to optimize the whole process itself. But when we talk about industrial scale fermentation process, we will use cost-effective complex substrate, meaning that the waste from other products as our resources and so forth. So you can find them derived from natural plant or even materials or even byproduct from the industry as our media base. Okay, why we don't use the pure chemicals? Again, we talk about cost. It's so expensive to use pure chemicals in industrial scale. We talk about 30,000 liters of fermenters, and you want to use the very pure chemicals for that. And because pure chemicals is expensive, the end product will be incur furthermore cost that will be so expensive to be commercialized afterwards. Because we are going to use raw materials as our resources for the media, so there are a few factors that we need to have a look. First of all, the cost and availability. So I know you might hear this word again and again, cost, cost, cost. That's what we thought industry is all about. It's about cost. So anything that you're going to decide in industrial world, you need to buy into the cost, whether you incur furthermore cost or not. So in this case, again, it should be inexpensive. And availability means that you can have that resources throughout the year. You don't want to be seasonal. For example, like, okay, we can only use these resources at Q3 of the year. So how about the other 3 quarters? So meaning that you can't do any production the other 3 quarters? No. You need to ensure that your resources for the media can be available throughout the year. Okay, and of course, the second one is to be ease of handling, regardless the media is in a solid form or even liquid form, because like you got it resources from other places. Okay, so that if you're talking solid might be much easier, but then for liquid, you want to make sure it's easy to be handled because it will involve transportation and logistic, etc., etc. And then in terms of sterilization requirements, you want it to be sterile, and then the process a simple sterilization step, and then you want it to not have any denaturation problems, meaning that you have, for example, carbon resources from palm oil industry, but then after 1 week you can't use it because like it might be worn out, it might be denatured. So you don't want that to be happening. You need to make sure that it will be stable prior to use for the fermentation process. And then we look into the formulation, into the mixing process, complex and viscosity of the resource itself, because like this will affect in terms of the agitation, the aeration, how much foam will be produced throughout the fermentation and downstream OTSP step as well. And of course, we want the media to promote the highest concentration of target product as much as possible. So we don't want it to only produce less than 50%. So you want to be higher than 50% because that will be much useful in terms of commercialized point of view. And then we want to ensure that the levels of racial impurities in the media is as low as possible. because if the impurity is too high, it will affect the growth or even the fermentation process. And overall, it should compliance with the health and safety point of view. You don't want the resources toxic. When people handle it, people die or got sick because it's too toxic to be handled, and so forth. So these are the example of carbon sources that you may find that compliance with the pharmaceutical fermentation industry. So some of it you can find whey or even starch or molasses, even fat and oils from other industry can be used as carbon sources for this fermentation media purposes. This one are the common nitrogen sources that we usually use as part of fermentation media. Soybean meal, pectin, even yeast extract, and some corn stick liquor. So it depends on the locality of your industry. So might be different in different industries. So this is quite common in the States and even in Europe area. But in Malaysia, it might be different because we have a different type of industry. You might use waste from the paddy industry. You might, for the rice industry, you might use waste from the palm oil industry as our nitrogen resources for the fermentation purposes. Okay, that's end about the media. Now we look into the system itself. So I mentioned earlier, we do the fermentation in a huge tank we call as fermenter, which they have a controlled temperature and so on and so forth. So the main function of fermenter itself, I mean, it provides the optimum or suitable environment that can help in terms of not just the growth of the microorganism itself, but also our main target objective is to have the highest efficient yield of our targeted product. So you can find the target product in the cell biomass itself, or even the metabolite of the fermentation process, or even you need to break the cells to get it, or even the bioconversion product itself. So that's the function of the fermenter. So how exactly you want to choose the best fermenter for your fermentation process? So these are the performance factors that you need to have a look. There are 5 of them. The first one is agitation rate. So you need to check what is the rate of the agitation process. And then oxygen transfer, how much oxygen needs to be used or no need oxygen at all. And the pH, whether you want to be acidic or basic or even neutral, and temperature. You want to make sure that it can keep the consistent temperature. Of course, you have a range, okay, but then you want to make sure that the range is very small and which it will not affect in terms of the fermentation process. And the next one is from production. Do you need a huge from production, or you need very less from production, or totally no from production? So that will affect in terms of how you want to choose the best fermenter for yourself. There are 2 point of view of type of industrial fermentation that we look. So the first point of view, we look whether it's aseptic or non-aseptic. So aseptic, you can find either in aerobic or anaerobic aseptic fermenter, or if you want to be non-aseptic, it can be aerobic and also anaerobic. So you can see some example here, like it's aseptic aerobic here. Most of the enzyme or RD proteins or even steroid I use this type. And how about the anaerobic aseptic? It's mainly production of alcohol or even lactic acid. So for non-aseptic, you can see it's more related to food production, even in terms of the wastewater management and so on. So in our case, most of it we're going to use in this aseptic condition because we are making related to medical product. The second point of view in terms of how to choose the types of industrial fermentation is either we wanted the cells to be in suspended mode or even in supported mode. So what is suspended mode? So the cells is growth like freely roaming in the media as individual cells, or might be as a flocks or aggregates. And if need to be in supported mode, you want the cells to be in a fixed film or even in still film, but then on the fluidized support, so they have some support. So you can see, but common that I will going to introduce to use is more related in suspended mode in this case. Agitation is one of the most important factors that you really take attention or pay attention to it, because like how agitate, how fast it is, how slow it is, how aggressive it is will affect into for the cell growth. So the agitation usually we use in the suspended cell fermentation. because the cell is like roaming freely. If you have too much high agitation, it might too fast, you might destroy the cells. If it's too low, instead of the cell agitate roam freely, it might just at the bottom layer of the fermenter. So also in the process itself, because there are so many phases in the fermenter, you need to make sure that the agitation in the fermenter can mix all of this. The liquid phase, which mainly the nutrients and metabolize, the gaseous phase, meaning that you provide oxygen and CO2, and the solid phase usually are the cells and or any other solid structure that may present. So you want the agitator, okay, that you can mix these three homogeneously as what to meet your objective. So if you want to produce homogeneous condition, and of course, because it's produced homogeneous condition, the nutrient, the gas heat transfer is well distributed throughout the fermenter. Here we'll introduce you three types of mechanism in agitation itself. So the first will be what we call as third tank reactor, or STR. So in this case, they got a mechanical agitator or impeller in the baffle cylindrical vessel. So meaning that it can be one agitator, one impeller, it can be two, three. Depends on the size and the purpose of your agitation process. So you can look, if you look into the image down here, the figure down here, so you have three set of impeller, so meaning that at different level, because like it's a huge tank. If you only have one impeller, for example, at the bottom, so you might not distribute homogeneously about for the top layer uh, of the fermenter itself. So we want to make sure that, as I said, homogeneous mixing is really, really important in this case. So for the STR, they use a mechanical agitator impeller, but then you have the second one, what we call it as a pneumatic system. So in this pneumatic system, the agitation process not involve any mechanical or moving parts. So how exactly they introduce the agitation? So they use the expansion of compressed gas to allow the mixing to be happen. So meaning that they pump the gas, so the gas, different pressure of the gas allow the mixture to be mixed around, to move it around to achieve the homogeneous condition. So the common example for pneumatic system for agitation is the airless fermenter as shown in this figure. Okay, the third mechanism of agitation, we are looking into hydrodynamic mechanism. So the word hydro there should tell you it involves liquid. So meaning that we use liquid kinetic energy in order to introduce or induce the mixing process in the fermenter itself. So how you're going to do? You're going to pump external liquid for external circulation and re-injection, meaning like the liquid itself we will circulate in order to allow the mixing to be happen. So the common one or the common example of the hydrodynamic mechanism is what we call as deep jet fermenter, as you observe in this figure below. So usually the one who monitor this fermentation process are the engineers or the technicians that are related to processing or manufacturing step. So there are 5 things that they need to pay attention in order to control and monitor the fermentation or the fermentation itself. So of course the aeration, you want to make sure the aeration is optimized as needed to allow the growth to be in a ideal condition. And the mixing, so the mixing must be allowed to have homogeneous. You don't want like only partial of the fermenters have the mixing but the others are not mixing very well, then it will affect in terms of your yield. And the temperature, it must be consistent, meeting your objective, and the pH also can be consistent, and the foam control. So I'm not sure whether you guys been exposed in terms of the food tech part. So when I was back in undergraduate, part of my biotech course, we learned how to produce sake, so Japanese rice wine. So part of it, like, it's really important for them to see the foam control, because for sake they don't want to have any foam, because like it will induce impurities and make the sake become bad. It can't be commercialized. But opposite with the beer production, which you want to have that foam that really tells you that this actually produce beer. That's why like when you, I know of course we don't pure alcohol here, but then if you look into the video, like when people drinking wine, for example, I mean sake, Japanese rice wine, there's no foam produced, just like really clear water, but compare with beer, when you freeze, like when you drink the gas, like the thick foam available. So the foam control is really important based on your target product. So if your targeted enzyme need to have foam, you need to measure how much foam, but it doesn't need to have foam, then it must not have the foam. So that's really important to do. So it doesn't tell you like you must have foam or not have foam. It depends on your targeted product throughout the fermentation process. So how exactly you develop the fermentation process? Of course, we're going to start back in the laboratory scale. So you don't start immediately to industrial scale or scale up if you don't ever optimize or understand the process in laboratory scale. So how exactly the laboratory scale of the fermentation process? So usually they still use a fermenter, but then it's the size about 1 to 10 liters maximum. And then in this step, we really do some examination studies of the media formulation, what would be the best, the consistent, the percentage of carbon, nitrogen, and so on and so forth for the targeted microorganism. In this case, we use feeding strategies, and then at this stage, we decide the most suitable type fermentation system afterwards when we want to do the scale up. And of course, laboratory scale, we use pure chemicals, but the scale up, we use more natural resources or natural derived resources. So for the scale up, so it's starting, we divide into two, we call it pilot scale and industrial scale. So pilot scale usually between 10 to 100 liters of the fermenters. Industrial scale can be 1,000 to 100,000 liters of the fermenters. So during this scale up, it's common to really experience decrease of product yields because like we use different type of resources, and then again this is not a linear equation process like from 10 to 1. If 10 you got 50 gram, 10 liters if you got 50 gram, if you say 100 it would 10 times more. No, that's not how it works. So it's not a linear equation, so you might find some decrease in the product yield. So there where the step comes to improvise to improve the whole process. And then because larger scale fermenters, it's hard to control in an ideal way. So and then they're usually not identical because it's huge, so the errors you introduce further more errors. So that's why like sometimes you cannot have really 100% equal or same condition throughout the fermenters. Even the same brand, the same size, you might find some different of the yield of the product. So that's the challenge in scale up. But then that's why we have the engineers, the technicians, the scientists working together to ensure that you have the target product within the range that you want to have. Okay, let me introduce some of the example through this fermentation process. So the common one is antibiotics. So antibiotics is usually generically being synthesized by industrial microorganism, and then most antibiotics available in the market right now, they got it from secondary metabolites. So not the primary but secondary metabolites, and then they are produced from different type of microorganism, usually fungi, specific filamentous, and even bacteria. So common or important antibiotics. I mean, I'm not going to teach you how many antibiotics are available out there, but then common being used through this process of penicillin, cephalosporin, aminoglycoside, or streptomycin. We know it, even tetracycline. So these are the common one that we can find available in the market, and also using this approach. So let me introduce one example, penicillin of an antibiotic. So for penicillin itself, so the process we use a fed batch process, and in terms of type of fermenters that we use stirred tank fermenter or STR or stirred tank reactors, and then usually the capacity of the tank itself between 40,000 to 200,000 liters. In terms of the processing, it involves starting from initial vegetative growth phase and then afterwards the antibiotic production phase, because you remember we are taking from the secondary metabolite, okay, not the primary one. And then you need to ensure in the fermenters you supply a optimum oxygen level between 25 to 60 millimolar per liter per hour. And then in terms of temperature, we keep it at 25 to 7 degrees, so more likely to room temperature, and the pH is more near to neutral, so between 6.5 to 7.7. So not acidic, not basic. It's really in the range of neutral pH. Okay, looking into the chart of penicillin production. Okay, so we took this industrial level. So we have the inoculum development and also production medium. So you choose the best cell strain and also choose the best medium, and then we go and call it production fermentation, aka a fed batch process. So after you've done the production fermentation, you go with the broth clarification. So the broth clarification, usually we do rotary vacuum filtration, and then in this step, after you've done the rotary vacuum filtration, you have two different, which one we got washed mycelium, so we're not going to use it for the penicillin. They will be used for other purpose, but then we're going to do only the solvent extraction of cell-free broth. Remember, we are taking for the secondary metabolites, right? We're not taking from the cell. So the solvent that we usually use is amyl acetate, and then we go to the next step, what we call as extract purification. So we need to extract the purified sample. So the example of the step that we're going to use, we use activated charcoal treatment and of course some filtration. Okay, after you got the purified sample, so you do some fraction purified sample, so it's in the liquid form. Okay, it's in the liquid form, so you need to crystallize them. So how you crystallize the antibiotic? By adding sodium acetate. So sodium acetate will induce the crystallization of antibiotics, so you have in the crystal form. And then here, how to recover it, because you need to separate between the crystal and the supernatant or the liquid. Then you go another filtration. So then you remove the filtrate, just take the crystal there. So of course, you need to wash the crystal. So usually we use the wash by using anhydrous ethanol wash, and then more filtration to remove any other impurities. And then of course you're going to dry them. So the drying, just a simple vacuum tray dryer. Okay, at this step, if you want to stop at the crystal drying, you already have what we call natural penicillin. So that's what we call it, natural penicillin. But if you want to do further modification, semi-synthetic penicillin that I've taught you guys much earlier in year 1, so we can do some treatment. For example, here they do penicillin acid treatment to add a new side chain in order to produce semi-synthetic penicillin. So these are the steps of the penicillin production. Natural penicillin, you stop at crystal drying. For semi-synthetic penicillin, you have another few treatments. For example, here penicillin acid treatment to produce semi-synthetic penicillin. Okay, that's the end of this lecture. So I'll appreciate that you guys do study this lecture, and then as I said, it's not much new for you guys. It's just more of the kind of like we revive back whatever that we learned back in year 1 and related specific to pharmaceutical industry. So that's it from me, and I wish you all the best. Thank you. Assalamualaikum warahmatullah.